Vitae, over there. So just as a bit of a warning, this talk is actually a talk that I'm giving tomorrow at an introduction to Git event that is also in this room. And it is all in Japanese. So all the slides are in Japanese, but I'm going to get to talk in English. So Japanese people, good, Ethan, that's great. English people, bear with them, and if you don't understand what I'm saying, ask, and if you don't understand what it says, ask, and I'll just get on. So today's talk is about the internals of Git. So can I just have a bit of a show of hands? Who here is sort of familiar with Git and knows it to use it? Okay, perfect. Yes. So, and who of those people know how it works under the hood? You know, sort of, what makes it all work? Probably only some sort of time as well. So, hopefully it'll be interesting. You don't need to know any of this. This is totally just. I think it's interesting.
Is there a test?
There's no test. You don't need to know this to use Git, I don't think. But when stuff goes wrong and weird stuff happens and you're in the middle of a rebase and you have no idea what's going on, it can help to figure out what's happening. So Git, what is Git? If you go man Git in the terminal, it'll say the stupid content tracker. That's the first introduction you get. And I think it's quite a good description, partly because sometimes it just feels really stupid and annoying to use, but partly because it is very apt. It doesn't do much. The basic model of Git is very, very simple compared to most other version control systems. It works in a very simple model, and it has the sort of basis that, well, we give you this simple model, and then using that correctly is up to you guys. You can mess it up if you want. But in terms of the actual features it offers, it's a distributed version control system. It has a lightweight branch model, which is one of the things that people push as one of the good things about Git. And it's well known for having a very obscure set of commands. There's actually over 160 Git commands. If you look at the full list of Git commands, there's now over 160. But the original version of Git that Linus Torvalds made in 2005 was only 7 commands. And you can actually do everything that you do now in Git just with those 7 commands and common Unix utilities. Everything else is just there as sort of helpers to make it a bit easier to use. So you're probably familiar with these sets of commands: git add, commit, push, pull, all the rest of it, stash, whatever. I want to talk a little bit about what actually makes those commands work and the commands that those are built on top of. But before I do that, I have to talk about the sort of fundamental thing that Git is made of. And Git actually deep down is not a version control system. It's actually a content addressable file system, which means, you know a normal file system, right? You have directories and file names. In fact, I've got a slide about now. You've got you give things a name, and you have read-write access to those things, so you can access things by their name and either read the data from them or overwrite it, or if you want, you can modify the data. You can read the data that's there and make some small modification and write it back. And you can also use directories to make a whole hierarchy. With a content addressable file system, that's not how it works. The name, the ID that you attach to a piece of data has a one-to-one mapping with that data itself. So if the data is different, the ID will be different. And that means that you can't have, the concept of read-write access doesn't make any difference, because if you modify the data, then the name will change as well. It has to change, because it represents that data directly. So, as well as that, you don't have any need for a hierarchy, because If you think about a traditional file system, you might have a file called food, for example, and there's a directory called bar that has a file called food, and a directory called baz that has a file called food. And those two files called food have different content. So that's why you need a hierarchy. Apart from the organizational thing, you need to be able to deal with the idea of two different files with the same name having different content. In Git, that isn't an issue at all, and in any content addressable file system. Because the file name is based on the content, you just don't need that. So there's no hierarchy, everything's just flat. So in tomorrow's talk, I'm going to give an example of showing how all that works, but I don't have time for today, so you'll just have to believe me. And that's basically it. That's the fundamental core of Git is that, and everything is built on that concept. So when we're talking about anything else, I want you to bear in mind that there's this content adjustable file system is at the core, and you're always dealing with a particular piece of data that is defined to be that and only that, and is unchangeable. In fact, it's quite interesting. It's immutable, and nothing ever gets deleted as well, if you think about it, because every time you modify something, instead of actually modifying it, it creates a new thing with a new name, and the old thing is left behind and still exists. If anybody's ever done any functional programming, there's a lot of parallels there, which is quite interesting. If you're into that. So there's three types of objects in Git, right? I've jumped a little bit. But on top of this content addressable file system, that on its own would not be very usable, because the sorts of file names that you get back are just like big hex strings. They're 20-byte hex strings. So like, commits in Git. You've got A2FE3021. Everything in the Git file system looks like that. So it's, on its own, it's not that useful. So in order to create a version control system on top of that content addressable file system, Git has an object model. And that object model consists of three objects: blobs, trees, and commits. So a blob is just a piece of data, right? So if you think about any file, it may be a text file or a binary file. It doesn't make a difference. But based on the contents of that file, you have a blob of data. I think I'm just going to give an example of this quickly. So you've got, this is my massive text terminal. I've got a sample project here. Say you make a file with some content, and you put it in a bar or whatever, right? So you've got a file called bar there. If you list the contents of bar, you get foo out, right? You're with me? If you then add that, you'll get an object in Git, which you can find by going Git objects, F, get a list of all the objects there. Like this. This is what you get for trying to do it live. Okay. It'll be fine. It's a good practice for tomorrow. You have blobs. This is actually the hex, the SHA-1 for an empty file. Because that blob's got nothing in it. Got sidetracked. You've got blobs of data, right? That is just data, and it's just the SHA-1 representing that data. But in order to actually access that data, if you had to remember the names for each piece of data, it would be really inconvenient, right? So you want to be able to, even though the content adjustable file system, the whole point is that you can use this SHA-1 ID in order to make it, in order to have a one-to-one mapping to be able to find the particular data for this one file. You actually do want to be able to use a file name, right? You want to be able to say, well, this is the file, my holiday.jpg or whatever, and be able to know that that file is the file you're looking for. And so in order to do that, you have the next Git object, which is the tree. And the tree is a really simple, it's just a text file which maps these SHA-1 numbers to the actual content themselves. And it gives them a name, and that's how you access them. So a tree is very much like a folder in a traditional file system. It can have other trees as members, but it doesn't. It doesn't have the whole hierarchy in one tree. One particular tree is one-dimensional. It's flat, and it just points to other trees. So this tree says, okay, I've got a blob. It's called new.jpg, and it has this ID. I've got another blob called git.text. It has this ID. And I have a tree, which is called back, and it has this ID. But it doesn't know anything about what's inside of that tree. This tree itself is a different Git object segment to that. Yes?
So how is the name associated to the blob data?
Okay. If I wasn't worried about messing up my console skills, I would show you. But basically, the tree is a very simple text file format which has the unit permissions, 6 decimal digits representing the read-write access to that file, followed by a space, followed by the name of the file, and then a null character, a literal 0, and then the 20-byte SHA-1 symbol, and then a new line and the next line. So that's how you pass that form. So that's trees.
So sorry, is each tree in a separate text file, or like?
Each tree is in a separate text file. Yeah, that's right. Each tree is so that that directory that I briefly went over earlier, before I messed it all up. These files here are all the objects that Git knows about in this particular repository. And some of them are trees, and some of them are blobs, and some of them are commits. And I was going to show you which one's which, but maybe it's in my history.
Basically, everything is a blob.
Yeah, right.
No, that's not true. Not in the Git terminology of blob. Okay, I've got a thing that lets me do that, and then I can do. This is quite daring. Yay!
tree.
I'm not going to go any further. But suffice to say that so this would be one of those files, and this would be another one of those files. So in this particular diagram, there would be a total of 5 files.
So each tree has a hash associated to it, right?
Correct.
Just like a blob would.
Just like a blob would, yeah, and that's important.
The difference between a blob and a tree being...
The first few bytes, that is either tree or blob.
Okay.
So you can look at those bytes and you know which type of object it is.
Okay.
And then you know how to pass it based on that. Okay. And that's cool because commits reference those trees. And commits are what you're all familiar with, right? When you do a git add and a git commit, they point to a particular tree. But what's neat about this is that in this first commit, we had a folder containing a file called git.txt, which had this data. We modified that data and did all sorts of stuff with it. In this commit, we moved this whole folder from our first commit into a subdirectory called back. Right? But the back entry in this tree points to this SHA-1 here. And so there's no repeated data at all. Like, it just directly refers to the data that already existed in the database. So that's how you get quite a lot of persistence. A lot of most commits only modify a couple of files in the repository. But the majority of the contents of the tree that commit represents already exists in the repository, and it can just refer to those SHA-1s that are already there in the object database. So that's how that works. And I've got a little summary on the contents of a commit there, which you're probably quite familiar with, but you've basically got the SHA-1 of the top level tree. You only need this SHA-1 because every tree underneath that is referred to. You get information about the parent commit, of which there might be more than one, because if it's a merge commit, you have 2 or more parents, depending on how many branches you're merging. It's also possible for there to be no parent commits, which is the very first commit in a tree. When you very first make a new Git repository, your first commit has no parents. And it's possible to have no tree, which is only for annotated tags. If you've never used those, you'll never encounter a commit without a tree. You get information about the author and when that commit was authored, the committer, and when that was committed. So that's quite an interesting thing about Git. It actually separates the act of writing the code itself and the act of adding it to the repository. And then you get a commit message. So, okay, we've got that. That's it. Those are all the objects that Git knows about. But there's another layer that Git has always used from the very start in order to get objects into the database and read objects out of it. And that's the staging area, which is also known as the cache or the index. So a thing that newcomers to Git often find a little bit surprising or different to other version control systems is that you have this 3-step thing where you've got to add the thing first, and then you commit it, and then you push it. And when you're adding it, what you're doing is putting it in the staging area, and then when you do a commit, that moves it from the staging area into your actual repository, and then when you push it, that puts it into your remote repository. So the staging area, when you're new to Git, it can seem like this kind of annoyance that you have to do this add before you commit every time. But I think it's quite interesting. It's actually been in there since the very first Git commit. If you do a Git clone of Git, you look at the whole history of when Git was first made, and obviously before Git was made, it was impossible to commit because it didn't exist. So Linus Torvalds wrote as much as he needed to in order to make the first commit. And that much was 7 commands and 1,000 lines of C code. Which, to put it into context, this talk is 800 lines of HTML, so it's nearly as long as the first version of Git. And this staging area was in from the start. That was part of his original design for Git. And the idea is that you add your changes into there as you're ready to start to commit them. And you can even, if you add changes into the staging area and you wipe your directory, you just rm-rf star, as long as it's not dot star, you can recover it. The staging area contains all of the data that is considered to be a part of the commit that's the next commit that's going to be made. So even if you delete all your data in your working directory, it's recoverable via the staging area. So that's everything you need to make it work, but to make it usable, there's one missing piece, which is you actually need a way to refer to these things. I mean, you've got these blobs, and they're accessible via the SHA-1s, but those are a pain to remember. So you've got a tree, you can use the file name to get the SHA-1 for a particular blob. But how do you get the tree? Well, if you've got a commit, then you can get the tree for that commit, and you can get the SHA-1 from that. But yeah, how do you get the commit that you want? Well, for that, you need refs. And refs are the model that are used for both branches and tags. So when you're dealing with your master branch or your remote origin master branch or whatever, that whole time you're dealing with refs. And refs are really super simple. I'm going to risk it again. So refs are a file that exists in the Git folder. That's all the refs. I've only got the master branch in my repository. If you cat git refs master, git refs heads master, it's just a SHA-1. It's just a file containing a SHA-1, and that SHA-1 tells you this. So this would be a file just saying 1.9AOC or whatever. So all a ref does is points to a commit. If it's a branch, then when you commit, it automatically updates and points to the next commit. If it's a tag, it doesn't, and it just continuously points to the same commit. That's the only difference between branches and tags. And that's all refs are. They're actually a sort of extra on top of Git. They weren't part of that original Linus Torvalds 2005 version of Git. And they're just a way of making it easier to find things. Yes?
If you modify manually the contents of that file, you can change it.
Yes, you can, yeah. If you point to the different, so
different
on this file, that's one. So this particular repository only has one commit, okay. So I've got 2 commits there, and my master branch is pointing at the second commit, and the other commit is C99. I should probably find out what that's actually called. 649, C99, and all the rest of it. Okay. So if I go to git refs heads master, and that's the hash of where it's currently pointing. If I change that to the previous hash, and I save and quit that, and I do that, that doesn't work. It's now, the master is now pointing to that. And the other commits being lost, because there's nothing pointing to it. That's the other interesting thing, is that all these files exist in the object database, but if there's nothing pointing to it, there's no way to access those files unless you happen to know the SHA-1. And so when you delete a branch, all that actually happens is that this file, that file in the refs folder, gets deleted. And all the commits and all the data that was on that branch actually remains in your repository. And it remains there for 30 days until Git automatically runs a command called git gc, git garbage collect, which will go through and look through your repository for any objects that are not pointed to by any of your branches, and it will delete them at that point. So even if you accidentally delete a branch and think you've lost all your work, if Git's ever seen it, it's safe for 30 days. It will remain in the object database until.
Is that 30 days guaranteed?
It depends on your settings. The default setting is 30 days, but you can change it to no days if you want.
Is there one per commit? Is there one tree object, or is there multiple tree objects?
There is one tree. Well, there's one tree object which may itself point to other tree objects. So a commit points to a tree, which is the top level of the hierarchy.
And if a subtree underneath changes, what does it point to? Does it point to the thing that's changed, or the top? Does it always point to the top?
It always points to the top one. Because if you think about it, if the subtree underneath changes, its SHA-1 will change, right? Because its content has changed. And the tree that points to it has that SHA-1 listed in it, so its content will also change and its SHA-1 will change in turn. Yeah. So that's it. That's all the objects you need to know about. That's the three, the blob, the trees, and the commits, which are the three objects. And then refs, which are just a convenience little file helper for getting to those objects. So on top of those, Git then gives you a load of commands, right? And its commands are divided into two. You have plumbing commands and porcelain commands. So very briefly, plumbing commands are sort of intended for scripts mostly, and they deal with the low-level details of the Git object model and all of that, and how that works. And porcelain commands are user-facing, and they're what you usually use. Git add, git commit, push, pull, stash, whatever. Those are all porcelain commands, okay? So that's the plumbing commands. Memorize them. There'll be a test next week. Interestingly, these 7.
Is that all of them?
This is all of the plumbing commands.
So all the porcelain commands are based on those.
Yeah. Yeah. And these 7 here are the original commands. The very first version of Git that I mentioned earlier, this is all there was. And that you did everything with those. And in fact, this isn't actually strictly speaking a plumbing command, it's a porcelain command, but I put it in there because it's one of those 7. But that's all you need to do anything you might do in Git, actually. Update index is how you deal with the staging area, moving things from the working model into the staging area. Diff file shows the difference between your working repository and what's in the staging area, so you know what to put into the staging area. initdb is Git init, they're synonymous. Wright tree takes the staging area and creates a tree object in the Git object database. And read tree does the opposite. It takes a tree object out of the Git object database, puts it in the staging area for you to read out. And commit tree creates a commit object and links it with that tree. And cat file is what I've been trying to use all evening with no success. And it just lists the contents of a file.
How would you add by using the update?
You would add using update index.
Yeah.
That's more or less equivalent to git add. And that puts it into the staging area, but that doesn't actually add it to the... Well, it adds the blob, actually. The staging area doesn't have the actual data. So when you do a git add, even, it creates a new blob. And the staging area just references the SHA-1 to that blob.
Could you, for the common normal commands like add, commit, push, could you say which plumbing commands get executed?
You should come tomorrow when I'm going to be talking for an hour, and I'll have a lot more time to do that. But that's what I'm going to be doing tomorrow, is going through some of the common commands and demonstrating the use of these. Just to wrap up, these are the common commands. These are the ones you probably know. But there's a load more. A lot of them are for dealing with other things like P4 deals with Perforce, there's an SVN one here somewhere there. So all of these commands are basically written in terms of the plumbing commands and other common Unix utilities. And that's about it. Very briefly, I've raced through it. I wrote this talk to be an hour. That wasn't an hour. So if there's anything you didn't understand, sorry, feel free to ask any questions. Yes?
Does commit contain the full file, or what is a diff technically?
So the commit just contains a single SHA-1, which is SHA-1 to the tree that represents the entire working directory at the point that commit was made. It's a snapshot of the actual state of the data at that point. And then that tree contains the SHA-1 of the files and the other subtrees and so forth. And so you can sort of regenerate the whole directory from that one SHA-1.
I have no problem about the tree. I have a problem about, my question is related to the data.
Mm-hmm.
So if I change some text in a file, is there like a new blob with the full content of the file?
Yeah, so semantically, yes. And in the original version of Git, yes. The Git is a snapshot-based version control system, not a diff-based version control system. So the idea is that every commit represents the actual full data at that point, and it points to SHA-1s that contain the entire blob of that file. But, as an optimization, since Git was invented in 2005, they've made something called pack files, which do actually encode that data based on diffs working backwards. So the
Like, is there an analog version of what, like, if you look at it, like, what would that be? Also, like, was there a forerunner? Is there competition? And is there anything that it fails at or is missing? And the etymology of Git.
What time is it?
Matt, what was it? Yeah. The etymology
of version.
Well, just real quick, if you could just answer this.
Okay.
Git. The word.
That's the least interesting question of all.
I know, yeah.
So Git, there's a thing in the README. He doesn't list one particular. The joke is, Linus Torvalds is quoted as saying, I name all the products that I made after myself. So first Linux was Linus, and now I've made Git because I am one. But I think there's another one, Global Information Tracker, is another sort post, what do they call them? Acronyms that you make after the fact.
Acronym.
Yeah, backronym, yeah, that's it. Yeah, so I don't think there's any one true etymology.
What was it? You looked it up yesterday.
Yeah.
What was it?
Okay, so for most Americans, we don't use Git in our
That's
language.
right.
It's British slang.
Right.
So Git is British slang for a stupid person. And that's why, what I read is, that's why they write it in the man page. Forget.
The stupid version. Right. Yeah. Well, stupid and... Well, not just stupid.
I think that's the closest American equivalent.
Yeah.
Right.
Yeah, it's more malicious than stupid. Yes.
Sometimes I thought that doing a push command is not the right way to update the Git system or something like that. So, what was your stance on that?
What, on pushing to a central server as opposed to pull requests and things like that? I don't have a strong stance. I think it depends on the project. So, I've contributed to open source projects on GitHub and things, and that all works through pull requests. And that's worked really well. Like, I've made contributions that people have just said, that's good, and taken straight away, and I've done others that people have said, you need to do this, or we can't take it. And that works really well. And I've also got my own projects that people have contributed to, and I like the peace of mind that they can just send me a pull request and I get to look it over before I accept it. But we're using Git here, and for us, until now at least, we haven't used, we came from SVN to Git, and we've tried not to make too many leaps at a time. So Git is quite a big leap in the first place. So to enforce pull requests on top of that, I think would be quite a big change to make all at once. So we've been doing it in quite an SVN-like way, with having one big server that everyone has access to, and they can just push directly to it. And in some situations, that's the best thing, because sometimes you want to be able to commit very quickly, and sometimes somebody in the corner shouts over, well, I need this thing right now, and you need to be able to just do it and commit it, and they can pull it and get it to them. On the other hand, you can actually do all that even if you're not using one big central server, because if you've got GitHub style, everyone's got their own version of the repo, you can just push to your version and they can pull from you. But that requires everyone to be quite good at Git and to know what they're doing, because they need to, knowing that you have as many remotes as there are people available, and you can choose which ones to pull from, and they're all going to be slightly different. And keeping track of all that in your head is an extra level of stuff to think about that you never had to think about with SVN or Perforce or any of those. So we're taking it one step at a time. And for us, it's working out okay. I'm also interested in Git flow as a model, which seems like the in-between of you've got some sort of control because you've got the development branch and the master branch, and you do all your fast, not very careful commits on the develop branch, but then the master branch is always stable. But you don't have the constant overhead of having to have somebody else look at the work before it can ever be seen by anybody else. So I don't know is the answer. I don't have a strong opinion. I want to try everything and see what works best in different situations. Yes.
Does the release of Git to change anything that you've said?
Not really.
Possibly not.
No, it's mostly a lot of the defaults for the porcelain commands have changed. So push, for example, used to push all branches that you had that had an upstream branch, whereas now it pushes the current branch by default. And there's a couple of other similar interface changes. But the underlying model hasn't changed since the original version of Git. One thing that has changed is that the index, the fundamental way, the idea of it hasn't changed. But Git's speed all rests on this. If this is slow, everything is slow, because this is the funnel by which everything moves. All communication between the object database and your real file system happens through here. So this is the bottleneck. So this needs to be fast, and it's been rewritten like 4 times, I think. I don't know which is the current version. I know there are versions 2, 3, and 4, which are all in general circulation. I don't know which is the most commonly used currently, but this is very commonly updated and changes wildly. It's incompatible with older versions. But the interface is the same. It's just the implementation. Anything else? Very good. So I was so fast and chaotic, but I hope you've got something out of it.